All right, so in this video, we're going to take a look at some examples, and the first one being this double integral given to us. And our job is going to be to convert this to polar and evaluate. Now, before we do that, I think it's worth noting that if we didn't convert this to polar and you're integrating with respect to y to start, it is somewhat of a challenging integral. It would actually be a trig sub, believe it or not. And so to avoid this, we would convert it to polar. And I don't think that that's a very hard thing to see, considering you have this x squared plus y squared sitting here. And if you look a little deeper into these numbers, these bounds, you'll see that the general region is something that polar is going to work great on as well. And so first thing I would do, something I did earlier when I first introduced this idea of either interchanging the order or now converting coordinate systems, I'm just going to basically identify what these things represent. And so first things first, since we have our y here and our x here, I know that I'm going to have things like x equals 2, x equals 1. I'm also going to have a y equals the square root of 2x minus x squared and y equals 0. That's going to be my basic region. Now, all of them are pretty straightforward except maybe this guy here. So let's take a look at this a little more closely. So if I square both sides there and move some things around, I'm going to get an x squared minus 2x plus y squared equals 0. Now, I left that blank there for a reason. We're actually going to complete the square here, so I'll put these blanks in. Half of 2 is 1, and I squared. If I put a 1 on the left, I put a 1 on the right. And then if you look closely here, what we've just done is said that x minus 1 squared plus y squared equals 1. So here we have a circle with a center at 1, 0, and a radius of 1. Now, again, I don't know that that's very difficult for a Calc 3 student to see, but it is definitely not, I wouldn't say obvious, to precisely what it is given this form. So running through these steps, I think, is definitely worth our time. So let me go ahead now and sketch what this region actually looks like. So remember, y is positive, so it's not going to be the full circle. It's just going to be the half circle. Looks something like this. It has a radius of 1. And that would be then 2, since we're centered at 1, 0. All right, so that's the big part of it. We still have x equals 2 and x equals 1. So that it seems like we're going to be dealing with this right here. And then we have y equals 0 as well. So this is the actual region now that we're needing to study. Okay, so when it comes to getting the double integral set up now, we know that this is going to be 1 over, and remember, x squared plus y squared equals r squared. So we have the square root of r squared, which would be r. So that's going to be a 1 over r. And then our dy dx changes into an r dr d theta. So we had to convert the function to thetas and r's, which in this case was just 1 over r. Our dA was the r dr d theta. And now it's up to us to figure out r equals, theta equals, theta equals. So now we're back over here to our region. So if I come out from here, let's say, and I'm going to be sweeping from here all the way around, and I've got my outer and I've got my inner. So in terms of the outer and the inner, let's go ahead and start there. You have to, again, think back to your polar days. The equation of this circle, the equation of this entire circle would be 2 cosine theta. So r equals 2 cosine theta. And then for the equation of this line, this one I don't know is necessarily one that we've used a ton, so maybe I'll go through it here. This would be x equals 1. We know that x equals r cosine theta, so therefore if I solve this for 1, or solve this for r, I get r equals secant of theta. So that's going to be the equation of that vertical line. So I'll come back over here. My outer was 2 cosine theta. My inner was secant theta. And this would need to be swept out starting from here, going up around to here, starting at 0, it looks like. And then to figure out what this is right here, I remember it would have to come all the way through and it would stop right there. That point of intersection would need to be found by setting our two functions equal to each other. So 2 cosine theta equals secant theta. So I'll do that over here in green. So 2 cosine theta equals secant of theta, which says cosine squared of theta equals 1/2. Cosine theta equals plus or minus 1 over root 2, and therefore theta ends up equaling pi over 4, which might not surprise you, but it is worth showing that this is how you would come up with that given some different situations. So 0 to pi over 4. So once again, this would be our setup now compared to this original one, and I am actually going to work this with you guys just to show you how it's done, but as I work it, it should be easier obviously than this, but don't lose sight of what this was. The whole point was to transition from the XY coordinate system into polar to make our lives easier. So I'm going to go ahead and clear the screen so that I have more work or more room to work on this problem. Okay, so I've just copied it down again and made some room. So first things first, very obviously these go away. And when I integrate then with respect to r, there will be that additional r that does pop up. So we'll have 0 to pi over 4, and then we'll have an r needing to be evaluated from secant theta to 2 cosine theta d theta. 0 to pi over 4 would give us 2 cosine theta minus secant theta d theta. And then we just evaluate these. The 2 cosine would go to 2 sine theta. And then the secant, that's one we studied in Calc 2. That's going to be the natural log of the absolute value of secant theta plus tangent theta, evaluated from 0 to pi over 4. So if I plug all that stuff in, I'll get a root 2 minus the natural log of 1 plus root 2 for our final answer. But the most important thing I wanted to show you then is compared to that previous integral in x's and y's, this was such a simple process. Now, of course, we did have to remember this integral, but assuming we do, this process is made. The whole idea of different coordinate systems is really to make your life much easier. So feel free to utilize it every opportunity you get. All right, so for this next example, we're going to find the volume of the solid bounded above by this thing and below by this thing. So when we get this set up, it's going to be that double integral. And then remember in a previous example, when it's not bounded by coming from the xy plane, where we actually have something, some function other than the xy plane that it's being bounded below by, we have to do the top minus the bottom. So for this one, above is going to be this and below is going to be this. So it's going to be this guy minus this guy. Now I can't just drop in this function right here, because if we're going to go polar, which we are, we can't have x's and y's. And so what I might point out to you briefly is that this guy here would be 15 minus 2, and then we have x squared plus y squared. So that's going to be 15 minus 2r squared. So when I put that in there, 15 minus 2r squared minus that minus 3. Again, that's going to be the upper minus the lower. You don't even have to graph these. It's telling you you're bounded above by this and below by this. So top minus bottom there. And then for the dA, that's going to be our r dr d theta. And we'll have our r equals here and here. We'll have our theta equals here and here. Now, again, much like the earlier example we worked when we had to do something like this, we need to figure out what our region is going to look like in R2. And this one's a little easier, whereas I can just now take the -3 and plug that in for my z value. Okay, so if I take the -3 and I plug that in for z, that's going to be -3 equals 15 minus 2x squared minus 2y squared, which is 2x squared plus 2y squared equals 18, or x squared plus y squared equals 9. Now, again, this says r squared equals 9, which means r equals 3. So it doesn't really matter how you view the graph. What it's going to matter is what you use over here. So we've got a circle centered at 0, 0, radius 3. Therefore, if we sweep this thing out, our r is going to start at 0, and it's going to go out to 3. So the inner would start here at 0 and would go out to 3, and then it would be swept around from 0 all the way to 2 pi. So 0 all the way around to 2 pi. So that would be your setup for that one. And again, I'm hoping you're seeing the benefits from having the polar coordinate system now available to us. It really, really does make things a lot easier in many scenarios. In fact, we'll introduce different coordinate systems here in a couple sections, which will hopefully make things even easier than they've been presented now. All right, so the last thing I'm going to mention in this video is the earlier example we worked, and it was the one where we had to do top minus bottom. And I mentioned that it's very, very difficult to integrate this in terms of x's and y's. But now that we have polar coordinates available to us, let's go ahead and convert this, and I'll really show you how much nicer it is. So right off the bat, this is going to be a root 2 minus r squared. So a root 2 minus r squared, and then we'll have a minus r squared. So that's going to be our r squared right there. The dy dx is going to turn into an r dr d theta. And then for our bounds here, the r, much like the last example, is going to go from now 0 to 1, and we'll go from 0 to 2 pi around. So much easier to deal with, not only in the bounds but in the functions themselves. And this distortion factor, this r, is really quite helpful, because when you distribute that in there, that makes this integral a substitution. Just let u equal the bottom and it's going to take care of the outside, or I said the bottom and the inside. Let u equal the inside and it's going to take care of the outside, and this would just be an r cubed. Without the r there, this would have been a trig sub, and this would have been just a standard power rule. But again, much easier to deal with. So as I pointed out, please take advantage of polar whenever possible.